Generalizing the proof for \sqrt $p, e.g., \sqrt $3. Welcome back, everyone. In our previous lesson, we walked through the formal step-by-step proof demonstrating that the square root of 2 is an irrational number. Now, you might be wondering if that specific method only works for the number 2. Well, the beauty of mathematical logic is that the method we used for the square root of 2 isn't just a one-off case. Instead, it serves as a universal template that can be applied to the square root of any prime number. So, in today's tutorial, we are going to extend that exact same logic to the square root of 3. And from there, we will generalize our conclusion to prove it works for any prime number, which we'll call p. Understanding the logic, the detective approach. Now, before we dive into the heavy algebra and the formal steps, I want us to take a moment to understand the underlying logic. It is very helpful to think of a proof by contradiction as being similar to a detective solving a criminal case. Imagine a detective starts an investigation by assuming a suspect is innocent. However, as the detective gathers more and more evidence, they eventually stumble upon a piece of proof that makes it physically impossible for that suspect to be innocent. Because that final piece of evidence makes the idea of innocence impossible, the detective is forced to conclude that the original assumption, that the suspect was innocent, must have been false. We are going to apply this exact same way of thinking to our math problem. In the next few slides, we are going to start by assuming that the square root of 3 is a rational number. If we follow the algebra and it leads us to a logical impossibility, a contradiction, then we have successfully proven that the square root of 3 must, in fact, be irrational. Step-by-step proof, the irrationality of \sqrt $3. Now that we have established our detective mindset, let's move into the actual algebraic work. We are going to prove that the square root of 3 is irrational by following a very specific, structured sequence of steps. Our first step is what we call the initial assumption. In a proof by contradiction, we start by assuming the exact opposite of what we want to prove. So, we will assume, to the contrary, that the square root of 3 is actually a rational number. Now, if it is a rational number, then by definition, we must be able to express it as a fraction. We'll write this as the square root of 3 equals a over b. In this fraction, we specify that a and b are both integers, and of course, b cannot be 0. But here is the most critical part of our setup. We must also assume that a and b are coprime. This means that the fraction is in its simplest form, and that a and b share no common factors other than 1. Keep this coprime condition in mind, because as we move into the next slide to manipulate the algebra, our entire goal will be to find a way to break this very assumption. Step-by-step proof, the irrationality of \sqrt $3, continued. Now that we have established our initial assumption in step 1, that the square root of 3 can be written as a fraction of two coprime integers, a $$ over b$, let's move into the actual algebraic work. In step 2, our goal is to get rid of that square root so we can work with the numbers directly. To do this, we square both sides of our equation. When we square the square root of 3, we are left with just 3. On the other side, squaring the fraction a $$ over b$ gives us a $$ squared over b$ squared. So, we have 3 equals a $$ squared over b$ squared. Now, to make this easier to handle, let's rearrange the terms by multiplying both sides by b$ squared. This leaves us with 3b$ squared equals a $$ squared. Let's label this as our first important equation. Moving on to step 3, we are going to apply a very powerful tool, the theorem on prime divisibility. If you look closely at our first equation, you'll notice that a $$ squared is equal to 3 times b$ squared. This tells us, quite clearly, that 3 must be a divisor of a $$ squared. Now, here is the crucial logical leap. According to the theorem on prime divisibility, if a prime number divides the square of an integer, then that prime number must also divide the integer itself. Since 3 is a prime number, and we have just shown that 3 divides a $$ squared, we can logically conclude that 3 must also divide $1. Keep this result in mind, because in the next slide, we are going to use it to substitute $1 with a new expression. Step-by-step proof, the irrationality of \sqrt $3, continued. Now that we have established that 3 divides a, let's move into step 4, which is the substitution step. Since we know that 3 is a factor of a, we can mathematically rewrite as 3 times c, where c represents some integer. Now, we are going to take this new expression for a and plug it back into our first equation, which was 3b squared equals a squared. When we substitute 3c in for a, the equation becomes 3b squared equals the quantity 3c, all squared. If we expand that, we get 3b squared equals 9c squared. To simplify this, we can divide both sides of the equation by 3, which leaves us with a much cleaner result. b squared equals 3c squared. This leads us directly into step 5, which is our second deduction. Take a close look at this new equation. b squared equals 3c squared. Just like we saw in the previous step with a, we can clearly see that 3 is a factor here, meaning that 3 must divide b squared. Now, we apply that same theorem on prime divisibility that we used earlier. Because 3 is a prime number and it divides b squared, the theorem tells us that it must also follow that 3 divides b. We are starting to see a very important pattern emerge here. Step-by-step proof, the irrationality of \sqrt $3, continued. Now we have reached the most critical part of our proof, step 6, where we identify the contradiction. Let's look back at what we have uncovered so far. In step 3, through our algebraic work, we deduced that 3 divides a. Then, in step 5, we followed the same logic and found that 3 also divides b. If 3 divides both a and b, this means that a and b share a common factor of 3. Now, think back to our very first step, where we set up our initial assumption. In step 1, we stated that a and b are coprime, meaning they have no common factors other than 1. We have now hit a logical wall. Our findings directly contradict that starting premise. This brings us to our final conclusion. Because our initial assumption, that the square root of 3 is a rational number, led us directly into this logical impossibility, that assumption cannot be true. Therefore, we have successfully proven that the square root of 3 is, in fact, irrational. Generalizing for any prime p $. Now that we have successfully navigated the specific case of the square root of 3, you might notice something very interesting. If you look back at our work with the square root of 2, the logical flow was almost identical. This brings us to a much more powerful realization. We can generalize this entire process. If we replace the number 3 with any prime number, which we will call p, the logic remains exactly the same. Let's walk through this generalized template together. First, we start with our initial assumption, just as we did in the previous steps. We assume that the square root of p is equal to a over b, where we explicitly state that a and b are coprime. Second, we perform our algebraic manipulation by squaring both sides of the equation. This gives us p times b squared equals a squared. Third, we apply that crucial theorem on prime divisibility we discussed earlier. Since p is a prime number and it divides a squared, it logically follows that p must also divide a. Fourth, to move forward, we use substitution. We let it equal p times k, where k is some integer. When we plug this back into our equation, we get p times b squared equals the quantity p times k, all squared. Expanding that, we get p times b squared equals p squared times k squared. After dividing both sides by p, we are left with the equation b squared equals p times k squared. Fifth, we look at this new equation and see that, once again, p is dividing b squared. Applying the same theorem, we conclude that p must also divide b. Finally, we reach step 6, where we identify the contradiction. We have now shown that p divides both a and b. This directly contradicts our very first step, where we stated that a and b were coprime, meaning they had no common factors. Because this logical chain holds true for any prime number you choose, we can state our general theorem. The square root of any prime number is always irrational. This is a powerful conclusion that moves us from solving a single problem to understanding a universal mathematical truth. Key takeaways. First, I want you to notice the template logic we've used here. Whether we are proving the irrationality of the square root of 2, the square root of 3, or even the square root of 7, the logical sequence remains identical. You don't need to reinvent the wheel every time. You simply follow this same structural pattern. Second, let's reflect on the role of prime numbers. You might have noticed that our entire argument relied heavily on the theorem on prime divisibility. I like to think of this theorem as the engine of our proof. It provides the necessary power to move from saying a prime divides a squared number to saying it must also divide the base number itself. Without the property of being prime, the entire logical machinery would simply stop working. Finally, remember the importance of the contradiction. The heart of this entire detective work we discussed earlier is the moment we identify a violation. The core of our proof is the realization that our initial assumption, that the numerator and denominator were coprime, has been broken. By showing that both numbers share a common factor, we effectively collapse the original assumption, leaving us with the undeniable conclusion that the number must be irrational. Now that we have successfully walked through the specific case of the square root of 3 and seen how we can generalize that logic to any prime number, let's pause and summarize the key takeaways from this lesson. In our next slide, we will look at some common pitfalls to avoid when writing these proofs in your exams. Common mistakes to avoid. First, be very careful not to forget the coprime condition. Throughout our proof for the square root of 3, we relied heavily on the fact that our initial assumption stated that A and B have no common factors other than 1. If you fail to state that A and B are coprime, you won't have anything to contradict in the final step. Without that contradiction, your entire proof falls apart. Second, a very common mistake is trying to apply this exact same logic to composite numbers. Remember, this method is specifically designed for prime numbers. For instance, the square root of 4 is not irrational because 4 is a composite number. If you attempt this proof using 4, you'll run into a logical wall. While 4 divides a squared, it does not necessarily follow that 4 divides A. A perfect example of this is that 4 divides 2 squared, but 4 certainly does not divide 2. This is why the primality of the number is the engine of our proof. Finally, when you are writing this out in a formal examination, do not skip the reference to the theorem. It is not enough to simply state that because 3 divides a squared, then 3 must divide A to earn full marks. You must explicitly mention the logic we used today by stating, since P is prime and P divides a squared, then P must also divide A. Explicitly citing your reasoning shows the examiner that you truly understand the underlying mathematical principles. Now, as we wrap up this tutorial, I want to pause and discuss some common pitfalls. Even when you understand the logic of the proof, there are a few critical errors that can cost you marks in an exam. That concludes our lesson on generalizing the proof for the square root of any prime number. Keep practicing, and I will see you in the next session.